morning. What is this? Good morning. Okay. Nice weather. Wish to sleep more, is it? Before to wake up. Do you have class before this? Yes. Anyone doesn't have 8 to 10? No. You know. So how about the rest? Because just now Dr. Wan told me there'll be a talk of 30 seconds of March. So he asked whether you guys can come earlier on 30 seconds of March. Yeah, it's like 9:40, 9:45. If you don't have class, then you probably can come earlier. So then there'll be a talk given by industrial people from China. Started from 10 to probably 10:45. Then only we will continue our class. In the week 5, 22nd of March. So you can come. You can come early, then you come now. All right, 22nd of March. Okay. So yeah. Testing. As usual, before we start chapter 3, can anybody give me some keywords for chapter 2? Some keywords for chapter 2. Goal. Okay, what is your goal? Yeah. You don't buy? Okay. You don't buy too early. First time I heard this kind of goal. Very good. Okay, so you had this goal. Goal what? Yes. Yeah, goal formulations. What else? Any keywords? Yeah, problem formulations. Yeah. So we have learned problem formulations. So what are the elements under goal formulations? How many elements? How many elements? 3. So can you list down these 3 elements? Someone said go, right, just now? Right, so you have go. On the ceiling. You? Abstractions, yeah, very good. One more. Go abstractions. Janice. Optimal solutions, right? Very good. So you have a goal, you have to define your destinations. You have to define the best solutions, either in the least number of stations, shortest distance, or a least number of times. So you have to define the optimal solutions, and lastly is the scope, right? So what are the factors you could actually ignore to focus, so that your agent can focus to achieve optimal solutions. How about problem formation? How many elements?
7.
What? 7, 1, 2, 3, 4, 5, 6, 7. So now, one by one. Initial state. DJ or Winnie. Path. Okay, very good. So you have initial state. That is a path, right? Okay, very good. So you have a path, definitely you have a path course. Right. Pui Pui, where is Pui Pui? I remember your name. State space, very good. So you have a state space. We have 3 more. Jeremy here. Hi, Jeremy. State space is stated here already. Start cost, very good. Two more. Jeremy. Successor functions. Alright. Very good. So successor functions, or we call it as operators, yeah, it's a function to determine where to go as the next move. And last one. Go test, very good. Okay, so you have 3 elements under go formulations and 7 elements under problem formulations, right? So once we have defined all these problems and the goal and also the problems, then we have to move to the next step to determine the strategy. Okay, so we have 3 strategies to apply. So once you have defined this, you have to tell the agents which algorithms to apply so that it can return you the solutions. So we have 2 main strategies here. The first one is known as uninformed search, and another one is known as informed search. Sometimes you can come across with other terms, like for example blind search. So this one could be called as heuristic search. Okay, so at the end of this course, you should be able to learn 4 to 5 algorithms of uninformed search, as well as how to determine or compare their performance. Alright, but however, we will only focus this uninformed search today. So this one we will keep for next lessons, which is chapter number 4. Alright, so under this uninformed search, there are 5 so-called algorithms here. We have 2 main algorithms, breadth-first search and depth-first search. So you just need to focus these 2. I think it should be sufficient. For the depth limit search, iterative and bidirectional search, they are actually variations from these 2 main searches, meaning that this 3rd, 4th, and 5th, they are the improved versions of the variations under this first and number 2. We can understand how first and the second, how it works, then you probably can understand the remaining algorithms. You don't really need to focus on the 3rd, 4th, and 5th, but you can just focus on these 2, breadth-first search and depth-first search. Okay? Alright, so let's move on to the first algorithm. It's known as breadth-first search. So before we move on to this algorithm, right, the step-by-step here, can you tell me what is the meaning of this word called breadth? And you have to, if you can understand this topic, this title, then you probably can understand the algorithm. Width. Okay, very good. So someone says width. Okay. What else? What is the definitions when you come with this word breadth? You can Wikipedia, you can search the dictionaries. What is the meaning of this word B-R-E-N-D-T-H? What is this? How to describe this? Quan. How to describe quan in English? White. White. Okay, white. What else? Starting. Okay, sure. So she described left to right. Alright, so you can see that all the description here is actually they are referring to horizontal, right? Horizontal directions. So width, white, from left to right, they are referring to horizontal direction. Meaning that if you apply these breadth-first search algorithms, we are the agent is going to search the successor from left to right horizontally. Alright, assuming that you have this state space. Okay, a very simple state space. So you like to travel from A. The agent have to search travel A to G. So if you apply breadth-first search as the name stated horizontals, meaning that you have to start from the initial state, which is the state A. So how it search? You're going to from the left hand side to the right hand side, you will scan. So if there is no more nodes that available at the right hand side, you will go to the next level. Okay, you will go to the next level, start to search B. Is it B equal to go? No. If not equal to go, you will go to the right hand side, which is horizontally. Go to check whether is it C equal to the go state. If not equal to the go state, go to the right hand side, check is there any successor here or not. If no successor, go to another level, check D, is it equal to G? No. Check E, is it equal to go? No. Check F, is it equal to go? No. Check G, is it equal to go? Yes. So stop here. So this is breakfast's work. If you ask how breakfast's work, what is the search path? The search path using breakfast's, it could be A, B, C, D, E, F, G. So this is how the agent search the path for you. Until here, stop. Then from the search path, it will give you return path. So return path is the path that seen by the user, right? So seen by the user, just like you are applying the apps Waze. So users, I would like to travel from A to G. So back end, this is how the agent search for you. So but on the screen, you will see A, C, and G. Where this is the shortest path that link A to G. So from here to here, A, C, and G. So you have two informations that you can obtain from this state space. One is a search path, one as the return path. Okay, so if you look at these algorithms, we begin with the root nodes. We start at this A, examine all the nodes in each level, so level by level. So we check these levels, okay, no more nodes here. Then we proceed to the next levels and repeat the process until you find the goal. Return fail if there's no solutions, right? So this is the animations of how breakfast's works from level to level. So level 1, level 0, so this is called depth 0. Travel to 2, 3, no solutions. Travel to another level, so 4, 5, 6. Travel to another level 7 and 8. So it examines level by level. That's it. Okay. So can you tell me what is the search path given this state space? Given that you are going to travel from R to O, how the agents return the search path and also return path. Okay, so the search path will be R, A, M, B, J, N, P, C, K, O. Stop. So this is how agents search the state space, right? So what is the return path? You have to find R, the nodes that joins the initial state and the goal state in the shortest stations, R, M, and O. So this is the return path. You are using breakfast search. Okay, so bear in mind, okay, although you are given the information here, 3, 4, 5, 2, 3. So although you are given this information, 3 kilometers, 4 kilometers, we are not going to use it to do the search, because always remember we are talking about uninformed search, meaning that the algorithm will perform the search without information given. Although the information is given here, but we are not going to use it to perform the search. So solely it depends on the patterns. Okay, can you see the patterns? It travels horizontally, go to next level, travels, go to next level, and travels. So it actually depends on the patterns, and it's not depends on the kilometer, the time given. No. Although the question given all the kilometers, you don't use it for the blind search. Okay, we perform based on the patterns. Alright. So this is another algorithm using depth search. So depth search always expands the deepest nodes in the current fringe, means that current branch of the search tree. note that leading from that end will be discarded from the memory. So then the search will back up to the next levels nodes that still have unexplored successor. So I use the same case here. I have A, I have B, C, D, E, F, G, H. Okay, so using the depth search. Okay, so what is the meaning of depth? What is the definition? Can you describe these words? Up to down, very good. Right, so we have up to down. What else? Deep, okay, deeper. Right, so based on these descriptions, you can actually imagine that that is actually one direction. So it's in contrast with this breakfast is horizontally, so this one is vertical. So it's totally different direction. What is from left to right? What is from up to down? So it's vertical. So how we perform this search? All right. So same. Start from the initial state. Okay. Start from the A. So as the names depth here, we travel from top to bottom. We don't really care what happens at the right hand side. We go to B first. We search, is it B equal to go? Not equal to go, so we continue to another level. We'll straight away go to another level. That's why it mentions expand the deepest node in the current fringe. So this is the fringe. So we are trying to search this branch first. If there are any solutions, okay, let's say D is not a solution. We are going to travel A to G. So D is not a solution. What happened? Back up to the next lowest node. So means that you do backtracking. You go back to the B. So check, do we have any left successors under the B? Yes, we still have one E here. We travel, we search. Is it E equal to solution? No. Alright, so then we do one backtracking. So B, do we have more successor under B? No more. We do backtracking to A. Okay, so it's actually going one direction. No, then only we go to the next branch. No, we go to the next branch. So we go to C here. Check C is equal to solution. No, we travel to F. Is F equal to solution? No, we travel back, and then we search. Oh yes, this is the go vertically. So it's not difficult to understand, right? So what is the search path? It's A. Search B, search D, no solutions, search E, no solutions, search C, search F, and search G. Alright, so this is the search path. What is the return path? In this case, is same as the breakfasts A, C, and G. Okay, so you look at this second sentence here. Note leading from that end will discard from memory. So what does it mean? It stated that if let's say we travel B, we travel D, right? So and yet this node, this branch, okay, is not going to give us any solution, right? Because we travel E also cannot get solutions. Go back B, go back here. So we know that this branch is not going to give you the solution. So basically these three nodes we can actually remove from the memory. So meaning that in the program later, you need to have a list to store all the nodes so that you can keep track which node to expand later or which node is already expanded. So let's say you have a B, C here, right? So and so on and so forth. So we know that this node is going to give you a solution. We can actually remove from the memory. Okay, D, E. So we can save memory. Okay, so that versus consume lesser memory compared to breakfasts. Breakfasts, we can't remove any nodes from the memory because we need to keep track. If you remove B, then we cannot expand the nodes from B because this breakfasts we expand level by level. Therefore, we need to store every single node in our memory. You can't afford to remove any nodes from the memory, right? So that's why breakfasts always consumes a lot of memory. Okay, you need to store every single node in your memory. So it consumes a lot of memory compared to the depth first search. Is that clear? So implement by calling tree using leaf 4. So it's the last in first out. So I'm going to show you what is the last in first out. So this is last in first out. So this is first in first out. Yeah? P4. Right, so that is the animations for the depth first search where we're going to expand the nodes branch by branch. So 1, 2, 3, no solutions. Go back one track, move back the next one level before this level 2 here. 4, 5, go back, 6, 7, 8. Right. So meanwhile the breakfast is 2, 6, 3, 4, 7, 5, 8. But back depth first 1, 2, 3, go back 2, 4, 5, go back 6, 7, 8. Okay. Is that clear? Good. Alright, so let's try some very complicated exercise. But before that, let's compare the performance here. So this is a theory. Theoretically, the performance, what is completeness? No matter you have a question like, okay, compare the performance for depth first, breadth first, you need to list down these 4 criteria. We compare in terms of completeness, whether these algorithms return you solutions or not. Okay, means that whether this breakfasts return these solutions or not. If yes, then yes, complete. Theoretically, breakfasts guarantee return you solutions, but breakfasts not necessary. Breakfasts may trap inside the endless loop because it's going one direction. If your space is too big, you will keep travels, but your solution, let's say, is somewhere around here, then you forever cannot get the solution because it trapped inside this branch. Right? It's not always. Optimality is whether optimality for this case for the price search, optimal solutions. Okay, for the price search is to travel or to reach the goals using least number of stations. Okay, for the breakfasts guarantee using shortest least number of so-called the stations. But for the depth first, it's not always. Sometimes you could get the optimal solution, but sometimes may not. Okay, but for the breakfasts, for the breakfasts, we guarantee because we travel level by level. That's why it confirm, it guarantee give you optimal solution. But for the depth first, not always. Okay, it depends on the case. So time, it depends. Okay, I'm going to show you later how to calculate or how to compare the time later on. But that is the proper way you're going to use these equations. But I'm not going to go that details. Meanwhile, for the space, as I mentioned, breadth first theoretically always consume more memory compared to depth first because you need to store every single node for each level. For the depth first, you can actually remove the memory that you know that this branch is not going to need the solution. You can actually discard from the memory. Okay, so that is the comparison. So let's move on to this questions, example number 2. So this is a very complicated space here. So you're given a lot of nodes from A to J. Okay, from A to J, so you have the numbers here, 4, 6, 2, 3, and so forth. Right, so you have all this value. But again, remember, so this is a prices. Prices, we are not going to use any information given. We just search based on the patterns, breakfasts horizontally, breakfasts vertically. So I'm going to show you how to perform the search and also generate the search tree, as well as the return path and the search path. Okay, so assuming that your goal is to travel from A to J. Okay, you're going to do. Hi. He's looking for agent. Okay, so you have a state space here, travel A to J. So how the agents perform the search? So let's say we use breakfast search first. Okay, so we have breakfast search. Okay, so we still remember last week we talked about that repeated states, right? So should we have a repeated state in search algorithms? Should we have a repeated state? No, right? Why? Any reason? Do you know what is repeated state? Right. Assuming that you can travel from A, you can travel to B. B in fact can travel back to A. Then you will forever trap inside these infinity loops. Right. So in the search algorithms, we always remember avoid this repeated state. Whenever the node that is already expanded, we don't store inside the memory. So I'm going to teach you how to keep track the repeated node. If you are given a very simple state space, you don't really need to actually use this technique to store the repeated state. But you have this complicated, then normally I will encourage you to create this two lists here. It's called open and the close, so that we can keep track the nodes that whenever it's already expanded, is not yet expanded, or is going to expand it. Alright, so what is open list here? Open list is a list, it's an array to store the nodes that's going to expand. Okay, meanwhile the closed loop is a place to store the node that's already expanded. I put expanded node. Okay, so one is going to expand, one is expanded node. So that we can keep track you have already expanded or not, so that we avoid repeated states. Okay, for the breakfast search, now let's start. So we start from A first. Okay, node A. So this one is the only node in the first level, right? So we put in the open list because this is the node that is going to expand, but not yet expanded yet. So now expand A. So once we expand A, we put it inside the closed list because this is the list to store expanded nodes. So the moment we expand A, what are the successors under A? B, C, and D, right? So we can actually generate B, C, and D. But before you put it down here, B, C, and D, we have to check the B, C, and D, is it inside the open list or not? You have to always check. If the node that is already inside this open list, we don't put inside the open list to avoid repeated state. So we have B, C, D, C, D is empty, so we can put B, C, D here. So we have B, C, and D. Okay, right. So next, continue. So we will always expand from the left hand side. Expand B. If you expand B, you get E and F, right? So before we put inside the open list, we check is E and F inside the open list or not? No. Then we can put where? You put behind. Okay, we put behind. So because this is behind breakfast, we add this node behind the open list. So we have E and F here. Continue. Expand C. If you expand C, you get D, G, and H, right? D, G, and H. But D is already here, right? D is already inside the open list, so we don't put. We add only G and H. Okay? So we add G and H behind. So meaning that C can go to D, G, H, right? So you can actually put a dotted line to indicate C can go to D. Okay, G, H. So I don't generate a new D here because if I generate a new D here, D can again go back to, let's say, I, then I would have a repeated state here. So I want to avoid repeated state, so I just put a dotted line to indicate C can also travel to D. So, okay, so we have that 0, 1, and 2. So again, repeat the process, expand D. Expand D, you get I, HI. Right? Follow alphabetical order. If we follow alphabetical order, it's H and I here. Okay. So again, so before we put H and I, we check. H is already here, right? So we don't put again because to avoid repeated state. So we can put a dotted line here and I. then we can put E, F, G, H, I. Okay, so we have level, 3 levels now. Expand E. Expand E, you get F. F is already here, somewhere around here already. So there's no more nodes that you can actually expand. E can actually travel to F, and then no more successor. So that end. That end. You cannot expand anymore. So it's okay. Continue with F. We always start from left hand side. Expand F. If you expand F, you get K. Only the only one successor, right? K. Right. So there's K here. So I add here G, H, I, K. Correct. Okay, G. Expand G, you get F and J. But F is already here, so we don't put to avoid repeated state and J, right? So we have J. G can go to F, so we can actually put a dotted line here. Okay, so we have J. H, I, K, J. So not yet reach the goal, because we are checking this. Is it equal to goal? Not yet. We continue expand. Is it equal to goal? Is it equal to goal? No. Continue to check. Is it equal to goal? No. Continue. H. Check H. Is it equal to goal? No. So we expand the H. H can give you L and G is already here. Okay, G is already here. So we don't expand. So we expand only L. I, K, J, L. So we have L here. Alright, so continue. Expand I give you L, right? But L is already here. So we don't put, we just put a dotted line and that end. Okay, so expand I. Okay, not yet finished. Right, continue. Expand K. Expand K, you get G. G again is inside here, somewhere around here, so we don't put it. So K can go to G. Right, so J. Okay, finally. Is it equal to go? Yes, so we stop here. So that is the search tree for Bradford search. If you are very good enough, you're familiar with all the how to draw the tree, you don't really need to show open and close. So I put open and close for you to so-called refer which node is already expanded, which node is going to expand. If you have a very complicated node, this is how the agent works. Okay, in the program you actually generate these two lists or the array to store the nodes so that we can actually expand and perform the search without trying a repeated state. So from here we can get some information. We have a return path, which is A. Okay, return path will be A, C, G, and J. Okay, meanwhile search path will be A. You can actually follow this. So this is actually a search path. Check. So you can travel A to B, B to C, C to D, D to E, E to F, G, H, I, K, J. So this is the search path. Sorry. Yes. We're going to find the shortest least number of stations that will join A to J. Okay, so you can A. So we stop now. So which one is the shortest? A, B, C, J, right? Is there any more way that we can travel? We can actually travel A, B, F, K, G, J. A, B, F, K, G, J, but longer path. It's not optimal.
given optimal solutions, we will sort this number of equations, right? So A, C, D, J will be this number of equations.
Yes, D is equal to go no, right? So then we continue with E. E is equal to go no, continue with F. F is equal to go no, continue with G. Continue. Until you see the J inside the closed list. Okay, so I give you 2-3 minutes to digest a little bit. If you're not really sure, then you. So mid breakfast is a first in first out FIFO FIFO. So because you add this first, then this is the first one, the first one that's going to expand. Alright, the first add and also the first one. Okay, so that's why it's called FIFO FIFO. Alright, so shall we move on to the depth search? Okay, good. So let's continue to depth search. Okay. So again, so let's say we create this open and close. So the process will be slightly different compared to the breakfasts, but since node open is going to expand, is the place to store the node that's going to expand. The close is the node that's already expanded. Alright, but instead of checking the node is already inside the open list, that first we check is the node is already inside the closed list. If already inside the closed list, we don't expand. If not yet inside the closed list, only we expand. So that is the difference. So this is check the open list, but this one is check the closed list. So let's start. So start from the A. So A is not able to expand, so we put here. Now we expand the A. So we expand the A, you get what? B, C, and D. So you get B. So C and D, I'm going to put a dotted line here. If you still remember how depth first works, depth first focus one path directions from top to bottom. We don't really bother the nodes at the other branch, right? So I put a dotted line so that if let's say there is a dead end here, no solutions. So if I backtrack to A, I know where to expand later on. Right, so whether you want to put, it doesn't matter. So I put here to alert me where to expand if there is a dead node here. So A, you get B, C, D. So I put B, C, D here first. So okay, at the same time I put a bracket A. It stands for, it's actually generated from A. So I'm going to show you why I put this bracket. Okay, C is actually from A, D is actually from A. So in the program, we have actually have this list to store this node as well, to identify C, which one is the parent node for C and which one is the parent for D. Alright, so now continue. Start from the left hand side, expand B. Expand B, you will get E and F. So expand B, you get E and F. Before we expand, we check E and F, is it inside the closed list? Is not inside the closed list, yes, we can put E and F. Okay, so now you have to put this E and F inside the open list. But we are not going to append behind, but instead we add in front. Okay, so the process is slightly different. Breakfasts we add behind, but breakfasts we add in front. So because this is so-called last in, first out. The last one they add in, but the first one to take out. So this is the first one take in, first one take out. So E, F, C, D. Alright, so this one B. Yeah. Okay, continue. So we expand E. You expand E, you will get F. Alright, you expand E, you will get F. But we check F. Is the F is already inside the closed list? Not yet, right? So that's why we can add this F here. Alright, so we can add this F where it's actually expanded from E. Okay. Okay, continue. So expand F, you get K. So check K inside the closed list? No, so we can expand. So we expand F. So you get K. Okay, so expand K, you get G. Expand K, you get G. So G is not inside the closed list, so we can add it. Add in front. Okay, so this one K. So after that G, expand, you can get J. So expand J is equal to go. Yeah, so we stop here. Alright, so the return path will be A, B, E, F, K, G, and J. So the search path also the same. In this case, so coincidentally they are the same. But there are some example, the return path and search path they are different. Okay, so you may see that the breakfasts give you guaranteed optimal solutions. It take only 4 stations, but breakfasts it take 1, 2, 3, 4, 5, 6, 7. A to B, B, E, E, F, K, G, and J. So there are 7 stations. It take longer stations, but it doesn't mean that it take longer distance. We are not going to take into account the distance. We just look at this station. Alright, so yeah, so you can say that this is a 4 station. So this is 2, 4, 6, 7. 7 station. Because this is deficit, so we just focus one part. Although because the F and from the B, we didn't expand, you know. Although the B, both E and F, right? The F is just a note that reserved inside the list. We don't expand. So although there is an F under the E, we focus that we give priority to E. But that is the
从我嘴巴讲出来才有灵魂。
No, if let's say F, you go backtracking, you B, let's say you backtrack, okay, no solution, you backtrack here. So this one we are not going to expand because we know that F lead you to fail. F doesn't give you solution, right? So F will eventually actually remove from the memory. Yeah. Then in the program we will write it's the expanded note. The note that's going to expand is already expanded. We remove it. We don't expand. Go to the next note. Okay, so is that difficult? Tough? Still okay? Alright, good. Okay, so let's compare their performance. Okay, so you have 4 criteria, right? So we have a completeness, we have the optimality, we have the time taken, whereas a space consumed. So you have 4. So now let's compare with the breakfasts and breakfasts. So complete. Breakfasts give you solutions or not? Breakfasts give you solutions or not? Yes, right? So that's what in this case, yes. I put yes. Breakfasts give you solutions or not? Yes, right? A, C, G, J, right? So give you solutions. As long as this algorithm give you solutions, the solution means that the destinations. Then we can conclude yes, completeness. Optimality, theoretically we know that breakfast is definitely optimal, yes. And it takes how many stations? A, C, G, J, 4 stations here. So how do we know that depth first search optimal or not? We have to use this value as reference. If the solutions for the depth first search also 4, we can conclude the depth first search optimal. But if the number of stations for depth first search is more than 4, then we can conclude depth first search not return you optimal solutions. Alright, so how many stations here? 1, 2, 3, 4, 5, 6, 7, right? So it's not. In this case, no, because it takes 7 stations. Okay, so let's continue. Time. So I'm not going to teach you that using the OV plus E one. That one is too complicated. So you just assume that every time you expand this node, you take 1 second. Assume. So you expand this 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. About 10 seconds. But this one, it's a 1, 2, 3, 4, 5, 6. Only 6 seconds. So you just expand only 6 times, right? So definitely depth first search take lesser time because less node to expand. Time for this one is more because you take more time to expand every single level. Every node at every single level. So you take more time. Right. Space, as I mentioned, depth first search theoretically take more. From here also you can see that you have to store every single node here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. You have to store 12 nodes for depth first search. How many nodes that you store for the depth first search? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Only 10. So it's also lesser compared to the breadth first search. Okay. So this is
Based on the case.
right. So I will give you a 10-minute rest. At the same time, if you want to try these questions, yeah. So go ahead. So this is one of the past year questions, 21, 22 May examinations. So the question stated you have a state space, yeah, A to I. So you would like to travel from A to I using breadth first search and depth first search. So you have to travel according to the rules, which is visited in alphabetical orders. You have to travel A, B, C, D, follow alphabetical orders, right? And then, yeah, no repeated state is allowed. Yeah, no repeated state is allowed. So you can try these questions. Else, yeah, you may take a rest for 10 minutes, yeah, and digest these questions.
If let's say J goes down to beta, there's no solution. And backtrack. So F is already expanded. So F has they are coming to same job. Program it. No backtrack. It should be expanded.
不要打粉，好。
分数。伊朗可是一下子就没有了。
是这样。
因为等下去做的话，你就会做了。
是在我手上。八字看一种语法。
Yeah, anyone wanted to try these questions? So let's try. Without the open and close, also I don't want to draw the open and close list. So I just explain. So A can go to B, C, D. Okay, so we start from the left hand side. Always start from the first note here. B can go to C and D. Yeah, B can actually go to C and actually go to D. So that end. No more expansions here. C can go to D and E. C can go to D and E. So again, let's see this in breakfast first. So we expand B already, C already, now go to D. D expand, you get to E and F. So you will get E and F. Okay. So E can go to G. Okay. Okay, and then go to F. F go to G and H. G and H. So G can go to I. Okay. So H can go to I also. So that is the solution. So the return path will be A, C, E, G, I. So the search path will be A, B, C, D, E, F, G, H, I. Okay, so depth first search. So A expand to B, B expand to C, C expand to D, D expand to E, E expand to G, A to B, B to C, C to D, D to E, E to G, E, F, G. Okay, and finally I. Okay, so that is the depth first search. So same travel path or search path and return path, they are the same for depth first search. Okay, so always remember follow alphabetical order because question stated visited in alphabetical order. So although the A, B can go to C and D, but we have to follow alphabetical order. Go to C first, right before D. So you cannot jump to D. If let's say in the program you didn't state travel alphabetical orders, then we randomly we let the agents to travel D or C. So they will decide. The agent will decide. But if we put already the one of the conditions is alphabetical orders, then it will just follow. And one thing I want to highlight here, if we go back to this question,
So, as I mentioned,
testing, okay, as I mentioned, so the optimal solutions here is refer to least number of station. So it doesn't mean that shortest distance is two totally different things. You look at this distance, we can actually still can calculate the distance. A to G is 6. C to I is 5 and 3, right? 5 and 3. So you try to add up 6 plus 5 plus 3, you will get 14 kilometers. Okay, but if you try to calculate the distance that travel from A, D, I, L, H, G, J. So A to D, you get 2, 2, 2, 1, 2, 3, right? So you add up together 6, 7, 9, 12. You get 12 kilometers. Okay, so it means that although it will give you the shortest, so-called least number of stations, it doesn't mean that it will return you shortest distance. Okay, so proven here, 14 kilometers. But this one take more stations. Okay, A, D, I, L, H, G, J, but it give you shortest distance. But always remember, this is blind search, uninformed search. So we are not going to use any information to perform the search. We just search based on the pattern. It's just based on the pattern. And our optimal solution for prices is always to get the least number of stations. Okay, so I hope that you can be very clear on this ideas. Difference, the shortest distance is not equal to the least number of stations. The shortest distance that you have to use the heuristic search that we are going to cover next week to show how the algorithm used to perform the search and return you the shortest distance. Okay. Okay. So can you help me? Thank you very much. Okay, so let's move on to the next one. I know that you already guessed. Yeah, so let's try with the simple one. Okay, simple ones using sliding puzzle. So last week, our students, our friends here, managed to solve the puzzle in the kind of 30 steps, already, right? And you stop in 20, 28, is it last time? 44 or something like that. So off, huh? Okay, so now I'm going to show you how do we actually can use this blind search to achieve the least number of slides using the blind search. So now we have this initial state 1, 2, 3, 4, 8, 5, 7, 6. So that is the empty space here. So always remember what is your successor functions: left, right, up, and down. So we have to always follow these successor functions. So let's try with the breadth-first search first. Okay, so start. So this is initial state, we expand. So we check this successor function. Can we move left? Yes. Can we move right? Yes. Can we move up? Yes, but we can't move down. So we can actually expand 3 successor here. Okay, right. So before we expand, we check is it equal to go. It's not equal to go, expand. Now check the first node here. This is because it's horizontally, right? So check this one. Is it equal to go? No. Then we should expand. So again, the moment that you expand to the next level, right? So you have to reset your successor functions. So check these empty tiles can move to left or not? Cannot. Move to right? Yes. Move to up? Yes. So we have 2 successor here. One is move to right, and then one is to move to up. Okay, but you will notice that this node is actually correctly. This one is 7 here. You will notice that this is actually repeated state. Right, this is equal to this one. So in any search algorithms here, we avoid repeated search. So by right, you should have open and close this to detect or to store all the nodes to avoid repeated state. So by right, this one will be actually removed because it's actually repeated state. So I just show here so that there are actually 2 possible successors, but since this is the repeated state, we are not going to store this in our memory. So we're not going to expand this in the next level. We will just expand this later on. So now go to this. Is it equal to the go state? Not equal to the go state, right? So we expand, can move to left or up. So there are 2 successors here. Left or up. Again, this is also repeated state. So this is actually we will remove from the list. So check this one. Is it equal to go? No. So expand. So this one we can actually expand 4 directions. So you should have a 4 successor here, left, right. So you have 1, 2, 3, 4, 5, 7, 8, 6. You have 1, 2, 3, 4, 5, 7, 8, 6. You have 1, 3, 4, 2, 5, 7, 8, 6. And last one you have 1, 2, 3, 4, 8, 5, 7, 6. So which one is repeated state? This one, right? So this one we actually remove. we expand level by level. Okay, so now, oh. Okay,
So now go to the next level.
go to the next level because there's no solution in this level. Go to the next level, check, is it this one equal to go? Not equal to go, expand. So we can move only right, up and down. So there are 3 nodes here. Right, up, and down. Okay, so continue with this one, check. Is it equal to go? No, expand. So you expand yourself, this one. Okay, check, is it equal to go? No, expand. Okay, not equal to go, expand. Okay, so this one you will get ref. Okay, so you will get 1, 2, 3, 4, 5, 7, 8, 6. Left, right cannot, up, yes. Okay, and then down. Okay, and then you expand. Okay, no solution, go to the next level, expand. No solution, expand, 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 go, 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 go until here. Until here. So this is actually equal to go. Then we stop it. Then we stop it. Okay, so your first part will be this. You will search, 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 search. But from the user side, we just need to slide from here. Okay, we have to slide up. We just move down here, and actually we move to the left, and then we move to up, down. So it's only 4 steps. Okay, so meaning that you can actually achieve the optimal solution in only 3 sides. 3 sides. Down, right, and down. Okay. So this is how we can apply the prices on this sliding puzzle to achieve optimal solutions using only 3 slides. Okay. Alright, so this is breakfasts. Let's move on to the breakfasts. So you have 1, 2, 3, 4, 8, 5, 7, 8, 6 again. So the successor functions, left, right, up, down. So breakfasts 1 direction. Go 1 direction. Move left. Okay, you can move left. Okay, so we have to continue to the next level. So we don't bother on the right hand side. Although you can, but we don't expand this. Continue. Okay, when you continue to the next levels, always remember reset your successor function. Can you move right? Cannot. Can you move left? Right can. But if you move right, it actually go back to this. So you will always track inside the loop, right? So this one is not valid. So we have to move into another so-called the successor function, which is up. 1, 2, 3, 8, 5, 4, 7, 6. So this is valid. Okay, so go to the next level. So when you move to the next level, reset this successor function. Can you move right? Can you move left? Cannot. Can you move right? Yes. So we move right. So this is what you will get in the next step. Then you continue. Continue until you get this. But it's going to take a lot of steps here for that purposes. Okay, but that is the algorithm. Using that purposes, we expand level by level. So from this level, second 0, 1, 2, 3, 4, 5, 6, it could be 30 or 40 steps using that purposes. Okay, so you may try these questions later on, but I'm not going to try this for you because it's going to take a lot of space here. Alright, so that is the comparison between breakfasts and breakfasts. Using a sliding tiles, yeah, I think it's proper to use this by search to give you the optimal solutions. For these examples, it is not encouraged to use prices because we want to have a path in shorter distance, right? As a user, we don't want to travel in the shortest station. There's no point, right? So for this case, I think it's more appropriate to use A star or using a heuristic search. We cover next week. So for the third example also, so it's not encouraged to use the prices. So next week we will apply the heuristic search to apply on this this example 3. You will see that how I'm going to apply heuristic to optimal solutions. So I will skip this example 3. Alright, so that's all for this breadth-first search and depth-first search. So this is another algorithm known as depth limit search. So this depth limit search is a variations under the depth-first search to avoid this so-called infinity loop. So remember, as I mentioned last time, just now, last week. So we have a A, B like C, then B. We fit inside this infinity loop, right? So what we can do here is we actually set the limit, set the depth limit. Let's say it's equal to 4. Then the search will only travel until like 1, 2, 3, 4. Stop here. So this is D. Stop at the level 4. Backtrack. Search here. Okay, backtrack. Search. Okay, search. So it will always search until level 4. It will not go down further. No. Because this is so-called depth limit search. We set a limit. Okay, so that we give a chance for the algorithm to traverse the node at the right-hand side. But the challenge for the depth limit search is there's no standard way to determine what is the appropriate or the optimal D. Right? There's no standard way. So you can use 3, you can use 4, I can use 5, you can use 10, but there's no standard vector. So how to solve it? You can use this iterative deepening depth search. So where we will try limit 4 first. If there's no solutions, alright, we add 1. Okay, we open this limit, we'll redo this search. Okay, go to the level number 5. Stop. Okay, search. If no more solutions, add 1 more. Okay, level 6. And so on and so forth. So this is so-called iterative deepening depth search. Okay, we search level by level. And last one, bi-directional search. So where we run the 2 simultaneous search at the same time. So for example, you have this 0, 5, 1, 2, 11, 7, 3, 6, 8, 9, 4, 10, 12. Okay, so you have a state space. So if you run this bi-directional search, we know that your initial state is 0. You want to traverse to a number 4 here. Okay, so we will start with I think 5. Sorry, it's not 0, 5. So we know that initial state is 5. Your destination is 4. So we will run breadth-first search at the same time. 5 can traverse 6, can traverse 7, can traverse 0. 4 at the same time, you run also. 4 can traverse 3. Okay, so the next state, 0. Because if you follow numbering system, 0 start first. 0 can travel 1, 2, 11. At the same time, 3 will expand to 1. So we meet at these positions. So we will stop the search and we will return the path 0, 5, 0, 1, 3, 4. So we perform the search from 2 directions until you come to a center point. Then we stop the search. Okay, so but however, as I mentioned, bi-directional search, iterative depth search, and also depth limit search are the variations from the depth search and breadth search. They are not really important. So pay more attention at the breadth search and depth search will be sufficient. Okay, yeah. So come to the part that you guys most happy ones, right? So when we come to the end of our sections, right? So next week we will cover the more difficult chapters, which is heuristic search. More calculations, more tree to draw, and yeah. Before this, before we end the class, so this is another partial question. You can take pictures and try by yourself. You can check the answer with me during tutorials or practical class. So that's all for today.
这牌给我吗？ 你还比我细。
随便拍的。
就是啊，为什么？我拿不到了？等一下。哦。
Taehyung, where is Taehyung? Taehyung, you're missing here. And also Francis. Francis. Not here.
Thank you. 谢佳薇。这个，它是勾处这个，对，它就是它的是纳箭头，纳箭头，这个是箭头头，它是 Jefferson 这个。我帮我解释，我懂它的原理，可我不解释。它这个箭头，它这边箭头，它都没有了当武器了吗？鱼后面都没有要走了，
跟猫娃一样的。
还没有那个呀，它直接走过去。
哎，就换了。